You know, every single day, our sun is throwing these invisible storms right at us. And while they can create beautiful auroras, they also pose a massive threat to our modern way of life. So, predicting them, it's not just some cool space science problem. It's absolutely critical to keeping our world switched on.
Yeah, we're not talking about your typical storm with wind and rain. This is the solar wind, a constant, powerful stream of charged particles blasting out from the sun. And when a big gust heads our way, it creates what we call a space weather event. And believe me, that's a direct threat to the technology we all depend on every single day.
And don't think for a second this is some abstract, far-off problem. A really severe space weather event, it could actually knock out power grids, kill the cell service on your phone, scramble GPS systems, and basically fry the satellites that run, well, almost everything. The stakes here are incredibly high.
So, how in the world do we protect ourselves from something like that? Well, you need an early warning system, right? And luckily, we have one. A kind of deep space sentinel, standing guard way out there, always watching for us.
The setup is actually pretty ingenious. About 1.5 million kilometers from Earth, there's this special gravitationally stable spot called the L1 point. And right there, we've parked spacecraft that act like weather buoys in a giant cosmic ocean. They sit right in the path of the solar wind, giving us our first heads up that a storm is coming.
So this brings us to the core of the problem, what scientists call the solar wind propagation delay. All that really means is the travel time. How long does it take for that gust of solar wind that just flew past our satellite out at L1 to actually get here and hit Earth?
On average, we've got about an hour. That's it. That's our entire warning window. Just 60 minutes to get power grids ready, put satellites into safe mode, and basically brace for impact. So getting that timing right isn't just important, it is everything. But here's the catch. Nailing down that 1 hour travel time is way harder than you think. Let's get into why our current methods sometimes, well, miss the mark.
For years, the go-to system for this has been something called OMNIWeb. It's the gold standard, and it uses all these complex models to predict the arrival time. And you know what? Most of the time, it does a pretty decent job. But when you're talking about a potential disaster, pretty decent just doesn't cut it.
So just how often does it struggle? Well, the research shows that in about 5% of cases,
The prediction is off by more than 20 minutes. Now, 20 minutes might not sound like a lot, but remember, you only have a 60-minute warning to begin with. Being wrong by a third of your total prep time is a huge problem. That could easily be the difference between protecting our infrastructure and, say, a massive blackout.
And this is where some brand new research comes in, offering a really exciting breakthrough. It's a smarter, much more reliable way to time these storms. It kind of moves beyond just the pure physics models, and instead uses a really powerful statistical trick.
The secret here is to stop thinking of the solar wind as just a smooth, uniform river. Instead, it has these unique, identifiable patterns in it. Tiny little fluctuations in its magnetic field and its density. So what this new method does is it takes a fingerprint of these fluctuations as they pass the L1 satellite, and then it looks for that exact same fingerprint in the data from a satellite orbiting Earth.
So, here's how this works. It's actually really elegant. The algorithm grabs a 20-minute fingerprint from the data at the L1 satellite. Then, it just scans through about 2 hours of data from a satellite near Earth, looking for a perfect match. The time difference between when it saw the fingerprint at L1 and when it saw it at Earth, that gives you an incredibly precise travel time. It's a simple concept, but wow, is it effective?
And I mean, just look at the results. They really speak for themselves. On these graphs, that blue line is the actual data measured near Earth. The black line, that's the old OMNIWeb prediction. You can see it's kind of close, but it's wavy, it's not perfect. Now, look at the red line. That's the prediction from this new fingerprinting method. It is a nearly perfect match. You can literally see how much better it is.
So what does all this new accuracy actually mean in the real world? Well, when you zoom out and look at all the data, the difference between the old and new methods becomes even more stark.
This chart says it all, really. Researchers measured the quality of the match with something called a correlation score, basically a grade for how good the prediction was. And as you can plainly see, the new fingerprinting method consistently gets a much, much higher score. It's not just a little better, it's a huge leap in accuracy.
Let's put some hard numbers to that. This new method, it finds a high-confidence match, a clear, unambiguous signal, in pretty much every single case. The old method, OMNIWeb, it only hits that same level of confidence about 72% of the time. That is a massive improvement in reliability. But here it is. This is the most damning finding of all. In a pretty big chunk of cases, we're talking 18%, the old system wasn't just wrong, it was confidently wrong. It was basically telling operators, hey, you can trust this timing, when the actual arrival time was way off. That is the absolute worst-case scenario, and it's exactly what this new method helps us avoid.
And all of this brings us to one final thought. We live in a world that is more connected, more digital, more dependent on really fragile technology than at any point in human history. Having a better cosmic stopwatch, one that's this much more accurate and reliable, isn't just a neat scientific trick. It's an essential tool for protecting our entire society. So the real question is, when that next big solar storm comes hurtling our way, will we